All right, last part of the note, or this is the last part of the notes for evaluating and graphing polynomials. Here are the steps for graphing, and then really the highlights or the most important parts of a graph of a polynomial. Many of these we talked about with quadratics. It's just now looking at them on a bigger scale, or the graphs get a little bit cooler and crazier. So to graph a polynomial, usually we'd use the TI-84. But I'm going to use Decimus in this demo, and you're welcome to use Decimus as well. So when I graph a function in Decimus, I'm going to, if I had to go on paper, again, we're kind of in a weird situation, so I won't make you graph on paper. But we are still going to find the turning points and the zeros. Remember, turning points are minimums and maximums where a function changes direction. So for example, a maximum happens when a function's going up, and then it reaches a high point, like the top of a roller coaster, and then starts going down. So this would be an example of a maximum. And then a minimum is just the opposite. So a minimum is when a function's going down, and then it changes direction. It has a turning point, and it starts going back up. So this would be an example of a minimum. And we've seen this with quadratics. Just some of these functions will have multiple minimums and multiple maximums. We also know zeros. We've seen that term before. That's the same thing as an x-intercept. So where is this function crossing the x-axis? And then we've also talked about end behavior this semester with quadratics. That means as x goes to the left forever, what's y doing? So I'll just give you an example with quadratics since we've done these. So for this left arrow, as x goes to the left forever, as it goes to negative infinity, it's also going to positive infinity forever. The other arrow, as x goes to the right forever, the y is also going up forever. So end behavior we've seen before. Again, these functions are just going to look crazy. And then 4, sketch a smooth curve. We'll see it. And then 5, we'll have to be able to note intervals of increasing and decreasing, which we've also talked about this semester. Increasing is when is the function going up versus when is it going down. And interesting enough, relating to part 2 here, those direction changes, increasing and decreasing, will happen at a turning point. So at a min or a max is when they'll change. So we're just looking at a couple examples. So the first one I'm going to graph, and I'll show this in Decimus, is negative x cubed plus x squared plus 3x minus 3. And I'm going to put that in Decimus here. So negative x cubed. And if you're kind of watching where I press, if you want to try using Decimus, it's pretty easy to use. So negative x cubed, let me arrow out of there. I already forget what it is. Plus x squared plus 3x plus 3. So plus x squared plus 3x plus 3. Let me double check. Oh, minus 3. Good thing I double checked. And let me shrink this calculator. So here I can hide the keypad. So I look at my function. This is a cubic. Its highest degree is 3. You see that right there. The constant, we talked about that's important. Negative 3 is the y-intercept. So there's the y-intercept, is 0, negative 3. That's the constant of this function. Other key points of this, let's look at the turning points and x-intercept. So here's a turning point. It's not pretty. It's not a nice whole number, but it's a decimal, but that's a turning point. It's a minimum, right? Because the function's going down. It's like I'm riding a roller coaster. I'm going down. I hit this minimum. I start going back up. And I start going back up until I get to this point. And here is a maximum. And at that maximum, I change to go back down. And I can't really write on this screen. Maybe I'll take a screenshot in a second. Other key points, besides here's the y-intercept again, at 0, negative 3. Here are my zeros, or my x-intercepts. So this is where it's crossing the x-axis. So here I have an x-intercept at negative 1.732. And then here I have 2 more x-intercepts at negative 1, or sorry, at positive 1 and positive 1.732. Let me just cut those out real quick. Just cut this section out so I can write on it. So here is that function that we just graphed in Desmos. Again, D-E-S-M-O-S. And the key points here from the notes, here's a minimum and a maximum. So here's a minimum. It's where the function changes from decreasing, as you see it's going down. Right, this whole interval it's going down, and then all of a sudden it starts going back up. So that minimum is a turning point. It's where it changes from decreasing to increasing. A maximum, so here's a maximum at 1.4.4 because the function changes from going up to going down. So that's a maximum. And then the zeros, here's a zero or an x-intercept. Is where it crosses the x-axis. And then I have two more zeros here. Sorry for my handwriting. And here's another one. Let's talk about end behavior of this function. Even though there's no arrows on it, end behavior, here's the left arrow. So let's talk about what this function's doing on the left arrow. X on the left arrow is going left. And the furthest left we can go is negative infinity. X on this arrow, Y on this arrow. So as X goes to the left, Y is going up forever. So that end behavior, and we write it just like that. So end behavior, I'm just going to write EB, is what's that left arrow doing? So that left arrow, as X goes to negative infinity, the Y is going to positive infinity. And then let's look at my right arrow. So I'm not done with end behavior because there's another end. So here's the right arrow down here. And this arrow, as X goes to positive infinity, or in other words, as this arrow goes to the right forever and ever, this Y is going down to negative infinity. So as that X goes to the right, this Y is going down to negative infinity. A little bit different than quadratics where the end behavior, the Y's always did the same thing. Here they could do opposite. So let me finish writing my end behavior. So the end behavior, as this arrow went to the left, the Y went up. The right arrow, as X went to the right forever and ever, the Y went down forever and ever. And that's something unique about a function that's odd. And this function is odd because the first term has an x cubed. So the cube, if the first exponent or the highest exponent's odd, that function's end behavior, these arrows, the Y's are going to point in opposite directions. Fun fact, if you think about parent functions, so with parent functions, if you remember the parent x cubed, let me pick some weird color. Here's purple. So if you think about the parent, f of x equals x cubed. It's been a while. Oops, but x cubed looked like this. It came up, it increased from left to right, the whole interval, and its intercept was at the origin. It should look familiar, it looked like a squiggle, right? So think about this function. So this is the parent, and you kind of see the squiggle in the red line. But notice the squiggle is opposite end behaviors. And guess why that happened? If I go back to the original function, what made that happen is this negative in the front. So the negative, just like with quadratics, reflected the parent. Meaning the parent, the purple function, usually increased, but because it's negative, it flipped, it reflected all those points. So that's something really cool how this relates to quadratics, at least in end behavior and with the reflections. So here's an example of a cubic polynomial. I'm going to do a quartic at a little bit faster speed to save time for you guys. All right, last example here of graphing a polynomial. Sorry, these videos are a little bit longer, but all you have to do for Thursday's assignment is take notes on these videos. So same notes here on the left, so no need to recopy them. But notice we have this new function, and it's a quartic, meaning the highest exponent is a 4. And I know last video I talked about odd, or not last video, a couple seconds ago I talked about odd functions having opposite end behaviors. When I show you this graph, you'll notice the end behavior ends up being the same. So it kind of looks like a quadratic. So I try to save a little time, and I already graphed it. So here's the same example. Notice the function kind of looks like a quadratic in the sense that it goes down and in the end it ends up coming up. But in the middle, there's a little extra crazy stuff going on. That crazy stuff comes from the middle of this function. So I got a little bit of cubic in there, I got a little bit of quadratic in there, and then my constant, as always, is the y-intercept. There's my y-intercept. I got some turning points and some zeros, so there's a turning point. The function's going down, and then at that point, negative 1.12, I start going back up. Here's another turning point, happens to be my y-intercept. So at 0, 4 is where I'm going up, and then I start going down. Here's an x-intercept at 1, 0, but I'm still decreasing. Then here's another turning point at 1.8, negative 4.3, because I'm going down. When I hit that point, I start going back up. I cross an x-intercept, and then I go up forever. So this is kind of the story of this graph. Let me get a screenshot of it. And I'll put it back in the notes, and I'll post these notes as well. So if I post this graph in here, try to fit it on with the notes. So here's my function. Let's look at the important points. So my turning point, so here's a turning point. This is a min because the function at this point is going down and then it starts going up. I have another turning point here at 0, 4. This one's a max or a maximum because it's going up and then it changes to going down. And then here I have yet another turning point, another minimum because it's going down and it changes to going back up. So this is a polynomial that has 2 minimums, 2 low points, 2 points where it changes from decreasing to increasing, and then it has 1 maximum where it changes from increasing to decreasing. So those are my turning points. I have x-intercepts here. Is an x-intercept or a 0? That's where it crosses the x-axis. Here's another 0. Another point where it crosses the x-axis. Notice the y-coordinate 0 because it has no height. End behavior for this function, if I look at the arrows, so there'd be an arrow here and here. So for my left arrow, my end behavior as x goes to negative infinity, the y, or this arrow, sorry about my handwriting again, is going up to positive infinity. And then this right arrow, as x goes to positive infinity, or as x goes to the right forever, the y is also going up forever. So my end behavior here, I'll write it down in my lower left quadrant. How it's written is exactly how I did, but a little bit nicer. So as x goes to negative infinity, y is going up to positive infinity. And as x goes to the right to positive infinity, the y is also going up to positive infinity. And then increasing, decreasing, I kind of mentioned as I went along, but these functions, like as I come in from the left, I'm decreasing. And I mentioned in terms of mins and maxes. Here at this minimum, right here is where I switch. So at this x coordinate, so from negative infinity to here, I'm going down. From negative 1.1 until 0, 4, until 0, I'm going up. So I'm increasing. And then at 0, I start going back down until I get to here at about just in front of 2 at negative 1.8. I'm decreasing. And at negative 1.8, I start increasing again forever. So I increase the rest of the interval. It's kind of like riding a roller coaster. I'm going to post an assignment tomorrow based on evaluating and graphing polynomials. So hopefully these notes will help. If you have any questions, as always, please just message me in the Remind 101 and I will get back to you almost immediately. All right, bye y'all.